Welcome to the first of several videos on paraxial ray tracing in optical design. I spent quite a bit of time learning this art, so I thought I would record it into some short video lectures and post them. I'll begin my description with a single thick lens where there's a front surface of radius R1 and a back surface of radius of curvature R2. C is the inverse of the radius, so typically radius is taken in millimeters and C is in inverse millimeters. N1, N2, and N3 are the refractive indices, N1 being in front and N3 being in back, and quite frequently they're the same, though not always. For example, if you're designing a cemented doublet, N1 and N3 will definitely not be the same. Frequently also N1 is 1, for example a lens in air, but still not always. N2 is the refractive index then of the glass. Little t is the thickness of the lens. This vertical line I've drawn is the principal plane. In the event of an equiconvex single lens, that principal plane will be right down the center. But in the case of a thick lens where the two surfaces have different radii, the principal plane deviates from the center plane. I'm going to consider just one ray of light. It's the marginal ray, which comes in parallel to the optic axis. This horizontal blue line is the optic axis. It strikes the lens and is refracted. It's called the marginal ray because it's at the margin. It's the farthest ray out in the problem I'm going to consider. There might be glass beyond that point, but I might have reasons later to throw away any light beyond the marginal ray, maybe with a stop. So the marginal ray is drawn this way. It comes in parallel, it strikes the glass, it refracts, goes through the glass, hits the back surface, and refracts again. The place where the marginal ray hits the optic axis is the paraxial focal point, and we'll do an example problem where we find that. Because each lens has different radii of curvature on each surface, you might have several lenses along an entire track that's quite long, in which case it's difficult to talk about the focal length of a lens system. We'll talk instead about the effective focal length, which is measured from the principal plane to the point of marginal focus, where this marginal ray strikes the optic axis. There's also the back focal length, BFL, which is the distance from the back vertex to the point of marginal focus. The derivation of the paraxial ray tracing equation begins by analyzing each surface individually. So let's look at the front surface. Consider an object in front of the front surface, a distance s sub 0 from the vertex of the front surface. When a ray comes from that object and hits the front surface, it is refracted down. Now, if we consider the case of this glass going on forever, then that ray refracts down and hits the optic axis at the image point. So the image distance s sub I and the object distance s sub 0 are depicted here along with the radius of curvature of the glass, the refractive index of the lens divided by the image distance, and the refractive index of the medium, m sub m, is the media, divided by the object distance. Makes a difference that can be related to the difference in refractive indices over the radius of curvature. So that's a working equation. Comes straight out of an argument from Fermat's principle, the principle of least time. And so we'll take that as a starting point here. And you can read about this derivation in several textbooks. Hecht has a nice description of the origin of this expression. Something that's different from a lot of optics textbooks is the sign that you'll find right here. You'll find a plus sign in most textbooks. And the reason why is because in optical design, a sign convention is adopted that's perhaps a little different from that used by other folks working in optics. The object distance is taken as negative when it's in front of the surface. The image distance is taken as positive when it's behind the surface. Another interesting consideration is the sign of the index of refraction. In the paraxial limit, where rays are taken as going either leftward or rightward, the index of refraction is taken as positive if the rays are going to the right and negative if they're going to the left. And in future videos, we'll have to actually use that sign convention. It won't come up here. There's the refracting power of the surface. The power is the difference in the indices between the two sides of the surface divided by the radius of curvature of the surface. And that equals 1 over the focal length. So if a parallel ray came in and hit this surface, it would focus at f. 1 over f is the power. So power is measured in per length per millimeters in our practice here. Power itself can be either positive or negative. In fact, for a lens, if it's positive, it's a converging lens, and if it's negative, it's a diverging lens. if the index of refraction of the media is less than the index of refraction of the lens, and if the radius of curvature is positive, as is depicted in this picture, then the power is positive. We can entertain 4 permutations on that, but here's another one. If the index of refraction of the medium is greater than that of the lens, and the radius of curvature is negative, which would be the opposite sense, it would be a concave, not convex surface, then the power is still positive. So you can generate for yourself the other 2 permutations that give negative power. But this is kind of important because these 2 scenarios that I describe here are the front and back surface of a lens. The front and back surface of a double convex or double concave lens will have the same sign of power, and we'll be able to add them together. Looking at the point where a light ray strikes the glass, Snell's law will determine the direction that light takes once it enters the glass. The red arrow is a ray of light. It strikes at a certain place. It's a common practice in optical design to consider angles relative to the horizontals. This horizontal dashed line is the horizontal, and all angles will be measured relative to it, not to the surface normal, as you may have learned in an elementary optics course. But I'll draw the surface normal because it follows the radius of curvature. Snell's law is written in terms of the angle relative to the surface normal. The index of refraction in one place times sine of the angle relative to the normal equal to index of refraction on the other side of the surface times sine of the angle relative to the normal. These 2 angles are both theta, and these 2 angles we'll call u and u prime. This angle is theta, so is this angle down here in this triangle, which I've shaded in. We'll stay with the paraxial approximation, which is the case that the angle of incidence is small. So all angles are taken as small. All angles are measured in radians in optical design, and in the paraxial approximation, then the sine and tangent of those angles equals the angle. And so sine of theta can be determined by looking at the shaded triangle. It's this height y divided by hypotenuse radius r. So y over r is sine of theta, it's tangent of theta, it's theta in the paraxial approximation. And so rewrite Snell's law using the small angle approximation. So instead of sine of u plus theta, just u plus y over r. So let's rearrange it a little bit. You have n prime u prime on one side. I recognize this n prime minus n over r factor as the power that we just talked about. Replace n prime minus n over r with the surface power phi. And that's paraxial ray tracing equation number 1. The law of refraction written in terms of the surface power and angle relative to the horizontal. If we want to talk about an optical system, we have several surfaces, and the light has to transfer between those surfaces. Here we have 2 surfaces. The light ray comes along and hits the first surface, refracts, moves through the new medium until it hits the second surface and refracts again. And in the paraxial approximation, we take these surfaces to be along the vertical dashed lines. I would like to know where the ray emerges when it arrives at the second surface. That would be what's labeled here as y prime. It's just the equation of a line, so y equals mx plus b. Y prime is t prime tangent of this angle plus y. T prime is what I'm going to call the thickness of the lens for a moment. Why? Because on the left side of an interface, we usually use a prime to denote quantities. The index of refraction, n prime. The angle relative to the horizontal, u prime. The distance to the next surface, t prime. And that's paraxial ray tracing equation number 2. PRTE1 was Snell's law incorporating the angle relative to the horizontal. PRTE2 describes the transfer of that ray to the next surface. And then when you get to the next surface, you go back and use PRTE1 to describe the refraction. And then you can use PRTE2 to describe the transfer to the next surface. You have this repeated use of these 2 paraxial ray tracing equations through a system that might have a lot of lenses. And so let's work on a problem using these 2 equations. We'll just do an equal convex lens. The radius of curvature is 300 millimeters for both surfaces. So R1 is plus 300 millimeters, R2 is minus 300 millimeters. Looking at the marginal ray coming in from infinity, although it doesn't matter where it comes from because it's horizontal, we'll have as a given a height of 10 millimeters above the surface. So you might take that as the radius of the lens as well, and at least the radius of the entrance pupil. And it strikes the lens and refracts and hits the optic axis at the point of marginal focus. Marginal because this is a marginal ray. Focus because that's where it's hitting the optic axis. We have various givens, thickness of 3 millimeters. For the material, we'll use NSF2, which is a fairly commonly used flint glass with an index of refraction at the D line of 1.647690. Let me comment briefly about all these significant figures in that index of refraction. You'd respect significant figures and never have any digits beyond the ones you could possibly know about, and to be able to state an uncertainty, and that uncertainty caps off how many significant figures you can reliably use. In optical design, it's necessary to use a lot more sig figs, so don't concatenate too soon. In optical design, we're frequently concerned with changes. When we proceed to calculate aberrations, we will look at the effect of a 1 part in 100,000 change in a distance, in a object height, and an index of refraction. Keep those, not because we can actually reliably calculate a position to a nanometer, but because we need to later be able to inspect the effect of a very small change in a quantity and look at the aberrations as well as the tolerance. There are two surfaces, and they will be the same, to the same sign as well, because surface 1 is found by taking the index after the surface minus the index before the surface dividing by r, and surface 2 as well, index after minus the index before. So the numerator flips sign between surface 1 and surface 2, as does r, so you keep your signs. So we have surface power of 00215, and yes, keep all those figures. Just for simplicity, I might look at the lens as a block of glass. Because the two surfaces have the same radius, the principal plane is right down the middle. So the effective focal length is taken from the principal plane to the place where the marginal ray strikes the optic axis, and the back focal length from the vertex of the back surface to the place where the marginal ray strikes the axis. A refraction occurs at point 1, then there's a transfer from 1 to 2, and then a refraction occurs at point 2. And what we want to do is find the transfer from point 2 to the optic axis and find out how far does the ray go. What is BFL, the back focal length? Let's look up close at these two surfaces and start to consider all these points. First, you have the marginal ray coming in parallel to the optic axis. So until you get to the first surface of the lens, nothing happens. So at the first surface of the lens, point 1, there's a refraction. When there's refraction, you use Paraxial ray tracing equation number 1. N prime is the index after the surface, so it's the index of the glass. It's that 1.647690. U prime is the angle after the surface, and I'm calling it U sub 2 in this picture. N is the index before the surface, 1. It's an error. And U is the angle before the surface, 0, because the light ray was coming along horizontally. And then Y is our 10 millimeters we were given as the height of the marginal ray, and phi is that power we calculated. So we have an angle after refraction relative to the normal of minus 0.1313. Now this minus sign is important. So if you have to rotate counterclockwise in order to get to the horizontal, then the angle is negative. All those sign conventions have to be consistent with each other. Now after the refraction at surface 1, the light ray goes to surface 2. So there's a transfer through this lens of thickness T. Transfers our Paraxial ray tracing equation 2 because it's just the equation of a straight line, so we can map out where that ray goes. The height above the optic axis, which is y, at point 2, at the final destination, is the height at the initial destination plus that angle times that thickness. Use 10 millimeters for the height at the original destination. Use the number we just got, minus 0.0131 radian, for the angle. After that 3 millimeter transit, we are at a height of 9.96. So then the ray has arrived at surface 2 and refraction happens, which means that we're back to Paraxial ray tracing equation number 1, applied at point 2. So you have an index before, which is the index of the glass, an index after, which is 1. The angle after, I'm calling U sub 3 in this figure, and the index before and the angle before. So the angle before, similar angles, U2 is also this angle made by the ray with the horizontal at point 2. Put in minus 0.0134 for the angle that is being made relative to the normal at point 2. And you have the new height, y, with the power again. So you get an angle of the ray after the final refraction of minus 0.043 radians. So now we need to follow the ray to the optic axis. Here in this picture, I extended it out, and we have our angle U3 here, which we just calculated. And the ray hits the optic axis, some unknown distance BFL away, but we know this distance here, y sub 2. You just do a triangle, or we can continue to use Paraxial ray tracing equation number 2, the equation for a line where the final destination is at a height of 0. So I'll have y prime equals 0 plus the angle and the thickness. T prime, we don't know what that is. It's the back focal length. We will use the expression, find the back focal length, and get 231.14 millimeters. And by the way, the effective focal length, which is measured relative to the principal plane, in this case is the back focal length plus half the thickness of the lens. That is not always the case. That's only the case when the two surfaces of the lens have equal curvature. Otherwise, that principal plane is not down the center. Go back and do all these calculations again, but with t equal to 0. I'll let you do that, but when you do, you won't get 232.64, you'll get 231.59. So now we can check it out. First, calculate the power of the lens. It's the index of refraction minus 1 times the difference between the two curvatures. But remember, one of the curvatures is negative. And you get 1 over 231.59 millimeters of the power of the lens. You compare that to what we found from our Paraxial ray tracing equations when the thickness is 0. Oh, they're the same. So to conclude, when the thickness of the lens is 0, the focal distance is the effective focal length, EFFL. And it's also the back focal length, BFL. So that's really about the simplest example I can present to you for using the Paraxial ray tracing equations to figure something out. You ultimately want to put it into a computer program or put it into an Excel spreadsheet, a YNU spreadsheet, YNU because Y and index of refraction and angle we call U. This is a YNU spreadsheet that we developed in the class that I took. It's time to make a plug for the optical engineering program at UC Irvine, which is absolutely an excellent set of courses. And if you need to learn optical design, this is really a good way to do it if you don't have the luxury of traveling somewhere and becoming a full-time student someplace. So our instructor in our first lens design course provided us with a skeleton of a YNU spreadsheet, and we spent the rest of the 2-course sequence building it out. What she gave us to begin with had these columns for a couple of surfaces, and it has a lot of stuff I've added to it. So each column is a surface. The first surface, surface 0, is where the object is. Certain information is important, such as t, the thickness, that is the distance after the object. So it's the separation of the object to the first glass surface, and is the refractive index in that region, and if it's an error, then let it be 1. There is something that is often used for computational convenience. It is not conceptually necessary, but it's this thing called tau, which is the distance divided by the index of refraction. I think it's called the reduced length. A given would be how high that marginal ray needs to be above the surface, and we just did it with a height of 10 millimeters. Another given would be the angle of that ray, and well, we made it a marginal ray, so it's 0. Always make that 0. You can calculate from that, the angle, but of course it's going to be 0 too. The angle, okay, so this omega is also for computational but not conceptual convenience. It's the incoming angle U times the index of refraction. They're both 0 here. I think I put the formula in U, user-defined value, in omega. Look at the second column of data. It pertains to the first surface. I have 2 numbers here. So 300 was input by the user as the radius of curvature of that surface, and then the curvature is calculated as 1 over that. The distance from the first surface to the second surface is t, and that was also provided by the user. It's 3 millimeters in our problems, and the index of refraction of the material behind surface 1 is provided. The power is calculated, and so we have a power of, hey, they even calculated the same thing we got, 002, the thickness of the lens divided by the index of refraction of the lens, and people like to call that tau. And the marginal ray height at the surface 1 is still 10 millimeters. I have a formula here for calculating the angle after the refraction using Paraxial ray tracing equation 1, which you can calculate from givens. That calculation is actually for n times u, and divide out n. Calculating the actual angle of incidence, which is relative to the surface normal. We don't use it in this particular problem, but it will show up later. And then there's one more surface. Surface 2 is the back surface of the lens. It has a radius I put in of minus 300 millimeters, and it calculates the curvature. And this t is the distance behind the second surface. This equation, so you can go and look at what those are. So we need to come back to it because it's borrowing numbers from down below. The power is calculated. Thickness is divided by the index of refraction, and the marginal ray height coming out of the back surface is calculated using the PRTE2, the transfer equation. And then the angle of the emerging light ray is calculated. So now you have a light ray traveling out of the back surface of the lens with an angle of minus 0.043 radians and emerging from a height of 9.96 millimeters. So from that, those two numbers can be put together to give you this 231.136 number. And so that's the distance the marginal ray travels before it hits the optic axis. I put that answer here. So that's just copied from this cell right here. So we have 231.136 millimeters. I do believe that's also what we got from our hand calculation. So that's the beginnings of the use of the YNU spreadsheet. In 22 weeks of course, we had a lot to it. I have the various invariants calculated down here and the aberrations, both geometrical and chromatic. And over the next few videos, I'll go through that a little bit. I strongly recommend that you make a YNU spreadsheet. Either use Excel or you can use MATLAB, works nicely. You can do your own programming in Python or Java. So there are two reasons why you want to make a YNU spreadsheet to do your optical ray tracing calculations. First one is the obvious one. If you don't have access to ray tracing software, you can write this into Excel. But the second reason, which I think is more important, is if you want to be an optical designer, you need to understand what's going on. The computer is not a black box, nor is the software that's been installed on it. You got to know what's happening under the hood. If you don't, you can't control what does and doesn't make sense. It's important, as you learn optical design, that you make a YNU spreadsheet. Don't use somebody else's, write your own and control it, and as you learn more, add on to it, like I did here. Okay, next time we'll add surfaces. So right now we just have surface 1 and surface 2, which gives us a single lens. But if I want to have an array of lenses lined up, I can add surfaces. That's not too terribly difficult to do with this. And then later we'll talk about the invariants and we'll talk about the aberrations. For now, I'll stop with that. Thanks for watching.